In the previous two lectures, I discussed how some stars at the end of their lives can form black holes, at least in principle. Specifically, we think that powerful gamma-ray bursts may signal the birth of black holes, either through the collapse of a massive star at the end of its life or through the coalescence of binary neutron stars. But is there actual evidence for the existence of so-called stellar mass black holes that form from such collapsing stars? Just because the equations permit their presence and some types of powerful explosions are thought to produce them, do they really exist? Are black holes science fact or fiction? Well, the only way to really be certain is to find actual black holes in nature. But given that light doesn't escape from black holes, one can't see them directly, so this might not be so easy, you know? Plus, recall that stellar mass black holes are small. A 10 solar mass black hole has a Schwarzschild radius of only 30 kilometers, about 20 miles. So viewed from a big distance, many light years away, such a black hole would look really tiny, just like a little dot in the sky. So it's not so easy, You can't just look up at the sky with your naked eye and see a black-looking region and say, oh, there's a black hole. It might just be a place that's devoid of bright stars after all. No, you have to use more sophisticated techniques. Now, remember how my supernova search team finds exploding stars? Well, we can apply the same principle here. We can take photographs of the sky and simply look for arrows. Look at that. There's a black hole, there's a black hole, there's another black hole, there's another black hole. Hey, it sounds really easy, right? Well, if it were that easy, we wouldn't give degrees for this kind of work. Here's a related cartoon by Sidney Harris. It's black and it looks like a hole. I'd say it's a black hole. If only science were that easy, That reminds me actually of another joke. Where do you find black holes? Well, in black socks. My students at Cal have to put up with me every day, right? Anyway, apparently black holes can also be found in some animals. Look at this, They're not spots, they're holes, this pig says. Kind of cute. All right. Turns out that you can see a beautiful looking black hole in the sky if you ever witness a total solar eclipse. Now, I've seen a lot of them. And to me, it's just striking how the sun looks like a black hole in the sky. But really, it's just the moon blocking the sun's bright disk, the photosphere, allowing one to see the beautiful, tenuous corona in its full glory. But it just looks like a black hole hanging there in the sky. It's just wonderful. Okay, well, we can detect black holes through their gravitational influence on other objects. In particular, black holes can be found in binary star systems with another star. They're gravitationally bound together, and they can betray their presence in the motion that they induce in the other star. So let's first consider a normal binary star with no black hole. Here are the two stars. They're orbiting one another. That is, they're orbiting their common center of mass. The blue star is 3.6 times as massive as the red star here, and they orbit one another. They both move. Now, these two stars might appear to be only one, even through a telescope, because they're so close together physically, and they're so far away that they simply merge together, even when viewed through a telescope. But if you pass the light of the combined light of these two stars through a prism, spread it out into a spectrum, you can see absorption lines, and in fact, you can see that there are actually two sets of absorption lines. In the spectrum that you see at the bottom, you can see the two sets of absorption lines produced by chemical elements in the atmospheres of the two individual stars. This is called a spectroscopic binary. The two sets of lines shift back and forth, as the stars orbit their common center of mass, and this is due to the Doppler effect. When one star approaches, its lines are shifted to shorter or bluer wavelengths because the waves of light are squished together. You've all heard this effect. When a siren is approaching, the pitch sounds high for the same reason. The waves are squished together, so their frequency is higher. Their wavelength is shorter, so they sounds like a higher pitch. Now, when the star recedes, its lines are shifted to longer, redder wavelengths because the waves are spread apart. Again, this is familiar with sound. The pitch of a receding siren sounds lower than when the siren is at rest. Now, if you hear a siren going ee-aw, 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 it doesn't mean that the driver can't make up his or her mind which way to go. It just means that the siren itself has a non-constant pitch. But as it's passing by, you can hear the high-pitched ee-aws go to low-pitched ee-aws, like that. Well, anyway, I'm not a very musically talented guy. So let's go back to the animation. Notice that the two sets of lines behave in opposite ways. When one set is blue shifted, the other set is red shifted. The two stars are moving in opposite directions. They shift back and forth as the stars orbit one another. If you increase the orbital speed, the blue shifts and red shifts get larger. The stars are shifted more. Their spectra are shifted more because of the greater speeds. But for a given separation between the stars, higher speeds mean larger masses. There's more gravity pulling on the stars, making them move fast. So by measuring the blue shifts and red shifts, as well as the orbital period, you can derive the masses of the stars, assuming you know the inclination of the system to the line of sight. Now, it's important to know the inclination because you need to know whether the measured radial velocity represents the total speed with which the stars are orbiting one another, or only part of the speed. Let me illustrate. If I have two balls here, and they're orbiting one another like this, and they're orbiting along your line of sight, that is, the orbital plane is along your line of sight, then the velocity you measure, the radial velocity, is in fact the full velocity. All right, it's the whole thing. Blue shifted, red shifted, blue shifted, red shifted for the case of the yellow star. But suppose now they're orbiting along some angle to your line of sight. Then only part of the velocity is the radial component, the radial velocity. That's not the full velocity of the star. In fact, if they were orbiting, in the plane of the sky, and I can't do that, I can't go through my hand, you wouldn't see any radial velocity at all because there'd be no component that's toward you or away from you. So simply measuring the speed doesn't tell you the full amount. It only tells you the radial component. So you need to know the inclination. And this means that when you measure double stars like this, if you don't know their inclination, you can only get estimates of the minimum masses of the stars because you only know part of the total velocity. Now suppose you look at the binary star and one of them is actually a black hole. Let's suppose the blue one here is actually a black hole. Then in fact you will see only a single set of absorption lines going back and forth, not two sets of absorption lines. But you know there's another object present there. There's got to be. Otherwise, the visible star wouldn't be in an orbit. Its lines wouldn't be going back and forth, Newton's first law of motion is that an object continues in its state of uniform motion unless it's acted upon by an external force. So something's acting upon the star, but you don't see it. There's nothing present. Well, maybe it's a normal but faint star, or maybe it's a black hole. Now, if you measure the orbital speed and period of the visible star, it is sometimes possible to determine the mass of the invisible object from Newton's laws of motion and gravitation. The catch is that you need to know the mass of the visible star from its observed properties. If you don't know the mass of the visible star, then in fact you can't figure out the mass of the invisible object. Also, again, you only get a minimum mass in general because you don't know the orbital inclination of the system. If the orbit is edge-on, then the minimum mass is the actual mass. If the orbit is inclined, then in fact the minimum mass is not the actual mass. Okay, so suppose you figured out that the invisible object has a mass that exceeds 3 solar masses, and yet it's not there, it's not visible. It's probably a black hole. A normal star in excess of 3 solar masses should be very bright, indeed often outshining the visible star. Yet you don't see it. And as I explained in lecture 2, we don't think that neutron stars can have masses that exceed 3 solar masses, 3 times the mass of the sun. Oppenheimer and his colleagues show that they gravitationally collapse. And white dwarfs, in fact, max out at about 1.5 solar masses, 1.4, 1.5, something like that. At that point, they have to collapse or explode. So something that exceeds 3 solar masses yet is invisible is a good black hole candidate. Now, the skeptic could say that it's not necessarily a black hole, since it could be 2 neutron stars bound together. This indeed is a valid argument, right? But suppose the mass is more than 5 or 7 or 10 solar masses. Then the case for a black hole becomes even stronger, right? It's harder to squish a bunch of neutron stars in a tiny little volume, all right? Well, where do we look? We can't monitor all the stars in the sky. Look at that. There's the Milky Way galaxy. There are millions of stars. We don't have enough telescope time to monitor all of these stars and look for these radial velocities. We need a clue. That clue is provided by X-rays. Now recall the electromagnetic spectrum. X-rays are a little bit longer wavelength, a little bit lower energy than gamma rays, and somewhat smaller wavelength, higher energy than ultraviolet light. We've had a bunch of X-ray observatories over the years. Most recently, in the past decade, the Chandra X-ray Observatory has provided a lot of really great data. It's been one of our best X-ray satellites. Now, a black hole or a neutron star can sometimes steal material from a closely orbiting companion star, producing X-rays from what's called an accretion disk of material. And those X-rays alert us to the system. Normal stars don't generally produce a lot of X-ray emission, and accretion onto a white dwarf generally produces ultraviolet light, not X-rays. So here's an artist's animation of one of these X-ray binaries where a compact object, a neutron star or a black hole, is accreting, stealing material from its companion. And that material heats up and glows as it goes toward the black hole, and it glows more and more at higher and higher energies, ending as X-rays very near the black hole. This picture always reminds me of this sort of heart of darkness. The heart of the accretion disk is this black hole surrounded by all this glowing light. So, this situation for some reason reminds me of Joseph Conrad's 1902 masterpiece, Heart of Darkness, though the context is obviously completely different. Cygnus X1 is one such X-ray source discovered in the mid-1960s, and it turned out to be especially interesting. A counterpart was found at optical wavelengths, and it turned out to be a bright, massive star, perhaps 30 or 33 times the mass of the Sun. Here it is, marked with an arrow. Well, spectroscopic studies in 1971 of that visible star revealed that it's orbiting something. It's orbiting something invisible. And the likely mass of that invisible object was at least 7 solar masses. This comfortably exceeds the 3 solar mass limit of a neutron star, and that object wasn't really visible. 2 independent teams found this effect, that the visible star is orbiting something that's invisible, but whose mass exceeds 7 solar masses. But for a long time, there was a lot of uncertainty as to what the actual mass of the invisible object really is. Estimates range between 7 and 25 solar masses. It's now known to be 8.7 plus or minus 0.8 solar masses. But for a long time, there was a lot of uncertainty because the conclusions depended much on the assumptions. The visible star is very luminous, it's very massive, but we don't know exactly how massive it is. It's interacting with a black hole, perhaps, so its properties could be affected. The problem is when you have a massive visible star, it complicates the analysis of the invisible star. So many people doubted for quite a while that Cygnus X1 was really a black hole. In fact, there was an informal bet between Stephen Hawking of Cambridge University and Kip Thorne of Caltech regarding whether Cygnus X1 really is a black hole or not. It turns out Hawking, who had spent his career working on black holes, actually bet against Cygnus X1 being a black hole, even though he actually thought it was. But he bet against it sort of as an insurance policy. If it turned out not to be a black hole, then his scientific work on black holes would have been wasted, but at least he would have gotten a nice little consolation prize, a magazine subscription. Now, he conceded the bet to Thorne in 1990 when the evidence regarding Cygnus X1 became really pretty secure. He was 95% sure that it was a black hole. A more unambiguous case of black holes can be found when you have a low-mass visible star in orbit around the black hole. If it's a low-mass star, not 30 solar masses, but less than 1 solar mass, then it turns out that the mass of the visible star is nearly irrelevant. Is it half a solar mass, 1 solar mass, 0.8? Doesn't really matter, doesn't complicate the analysis. Because when the visible star has a low mass, it turns out that the equation for the minimum mass of the invisible object, the presumably more massive object, is just the cube of the orbital speed multiplied by the orbital period divided by 2 pi and Newton's gravitational constant g. So you just need to measure the maximum radial velocity v and the orbital period p. Plug it into the formula, you get the mass m, or at least the minimum mass. Well, how do you find such systems of a low-mass star in orbit around a potential black hole? You scan the skies at X-ray wavelengths and look for stars that undergo a giant burst in X-rays. X-ray novae, they're called. A nova is a new star, nova stella. But not really. It's an old star. It just brightened in the X-rays. These systems are thought to be binaries where one star is dumping material onto a compact, dense other star. Perhaps a black hole. You see this accretion disk and it's orbiting something compact, emitting a lot of X-rays, could well be coming from a black hole. Now, if a blob of gas suddenly gets accreted onto the compact object from this disk, instabilities form in the disk, producing blobs, then you get a burst of X-rays. It's like an apple falling and hitting the floor. A burst of energy is released. It's hard to measure, but when you have blobs falling near compact, massive stars, then there's a lot more energy than when an apple falls on your table. So you look for these bursting objects. They become bright at other wavelengths as well, like optical wavelengths, because the accretion disk becomes full of light that's being emitted from the whole thing. And, it brightens all over the place at all wavelengths, and then it begins to fade. So you wait for it to fade, and when the light is largely from the donor star, then you can get a spectrum of that star. See whether it's going around something massive, figure out the mass, and determine whether it's likely to be a black hole. Now, my research team at Berkeley is interested in finding stellar mass black holes, so we eagerly await the discovery of X-ray novae of this sort. The first one that we studied in the mid-1990s was called GS2000 plus 25. It was discovered by the Japanese Ginga satellite. It became bright at all wavelengths because the accretion disk was glowing at all wavelengths, but it gradually faded. And we watched it fade, and then we took a photograph showing the star in quiescence. It was no longer bright because of the accretion disk. Now the light was dominated by the star itself. We used the mighty 10-meter Keck telescope, the first one of 2, on Mauna Kea volcano in Hawaii, took a series of spectra, and analyzed the results. Now, the top spectrum shows the combined data from all of our spectra of this GS2000 plus 25. And you see, in addition to a big fat emission line due to hydrogen, you see a bunch of little narrow absorption lines. They resemble the absorption lines formed by the atmosphere of a normal star, as is shown in the bottom spectrum. By analyzing the individual spectra, you could see that they shift one to the other. The wavelengths shift. Now, these spectra look kind of noisy, but when you do a full analysis, you can tell that there's actual signal there. And we plotted the radial velocity curve, and here it is. What a thing of beauty. You can see that initially the visible star was moving away from us at about 520 kilometers per second. Then, a little over 4 hours later, it was moving toward us at 520 kilometers per second, a negative radial velocity. Then 4 hours later, away from us at 520 kilometers per second, and so on. This is a beautiful sinusoidal curve that describes circular motion. And when you analyze the period and the velocity, figure out the minimum mass, you find out that the star that it's orbiting, or the object that it's orbiting, has at least 5 times the mass of our sun. Possibly, we thought at that time, up to 14 times the mass of our sun. We now think it's more like 8 or 9. So the headline that came out was, UC astronomers observe black hole in the Milky Way. And the subheading is, it may be 14 times as dense as the sun. Well, they got it a bit wrong. What we meant was that it may be 14 times as massive as the sun. Okay, well, remember that you only get a minimum mass from these kinds of measurements. To get the true mass, you also need to know the inclination of the orbit. And you can do that by measuring the brightness of the visible star as a function of time. Here you can see such a plot. The star got brighter, fainter, brighter, fainter. And this is because the star is actually elongated. Material is being stolen from the star by the black hole, and it's also stretching the star. And if you look at the star in this configuration, the cross-sectional area is large, so it looks bright. But as it orbits, you will sometimes see the star in this configuration where the cross-sectional area is a bit smaller, and so the star looks fainter. And then in this configuration, the area looks bigger again. Now, obviously, if it were orbiting in the plane of the sky, then the cross-sectional area would not change. And so the amount of change depends on the inclination of the orbit. And by measuring the light curve in this way, we can estimate the inclination. We can also then figure out how much the star really weighs. If we know its minimum mass and we know the inclination, we can figure out more probably the total mass. And the result for GS2000 is that it's between 8 and 9 solar masses. So the dark object is that massive. It's very difficult to have a cluster of neutron stars all bound together within a little tiny volume orbited by a star in only 8 hours. So the most likely conclusion is that this really is a black hole. If there were a bunch of neutron stars within the volume of the orbiting star, they would quickly converge to form a black hole anyway. They would be gravitationally unstable. So, this is really cool. A black hole, 8 to 9 times the mass of the sun. Well, we now know of about 24 such stellar mass black holes, and my group at Berkeley found several of them. Here's a diagram of, or a schematic showing their configurations. At the upper right, you can see the distance of Mercury in our own solar system from the sun, about 0.4 astronomical units, or 40% of the 93 million miles, the distance between Earth and the sun. And you can see that these systems are basically, that same size, typical orbit of Mercury around the sun. And some are even smaller. The one at the lower left, called QZ Vulpeculae, that's just another name for GS2000 plus 25. So that one's really just a little guy, even compared with our solar system. So it's really neat, looking at these things. And, we announce these things at conferences. And in fact, there's a joke I saw once, a cartoon, where the astronomer is announcing a black hole to a conference, and he says, "You can imagine my surprise when repeated spectroscopic analysis demonstrated that black holes are actually very blue." He said something like this, Well, they're not blue, they're black, but anyway. Well, a very new result, announced in October of 2007, was a stellar mass black hole in a galaxy about 2.5 million light years away, a galaxy known as M33. It's in our local group of galaxies, but it was notable in that this was the first black hole in a galaxy that was not the Milky Way or the two Magellanic Clouds, the two main dwarf galaxies that orbit the Milky Way. So this is a really external galaxy. The other weird thing about this stellar mass black hole is that it was about 16 times as massive as the sun. So we were alerted to its presence from the X-ray image. Here you can see the optical image compared with the X-ray image. That pinpoints the location of the object, and measurements by Jerry Orosz and his collaborators at the San Diego State University showed that the visible star is 70 solar masses, one of the most massive stars known, and it's being orbited by a black hole 16 solar masses. At that time, the most massive stellar mass black hole. That's kind of cool. On the other hand, if you look at this impression, we don't really know that this is what it looks like. These are artists' impressions. We would love to see these black holes in such detail, but right now we can only infer basically the presence of the black hole and the approximate properties of the massive star. Mind you, we've never seen such details as are often shown in newspaper and magazine articles. Okay, well, the fame of this M33X7 object was fleeting, because just 2 weeks later, a group of astronomers at Harvard announced that they had found a roughly 30 solar mass stellar black hole. And that was just 2 weeks later. That was found in a galaxy called IC10, a scrawny-looking galaxy like this. There were reasons to doubt this conclusion that they had found this black hole because, in fact, one key spectrum that the researchers used was suspect. It had a flaw in it. Moreover, the mass and orbital parameters were quite uncertain, even if correct. So my student, Jeff Silverman, and I used the mighty Keck 1 telescope again to get a series of optical spectra to refute the result, or, if it's correct, to confirm it. So here you can see on our optical guide camera image the optical counterpart of this X-ray source. We took a series of spectra, and lo and behold, we found that it had emission lines that shifted back and forth, back and forth. The visible star in this case is a weird kind of a star, 35 solar masses, we think, in mass, and it produces emission lines, not absorption lines, but the point is that they vary with time. You can see the position of the line varying. And the radial velocity curve we came up with showed an orbital period of 35 hours and a maximum radial velocity of 370 kilometers per second. The result? This is roughly a 30 solar mass black hole. The uncertainties are such that it could be between 23 and 34 solar masses, but basically the Harvard group was right. They didn't have very good data, but sometimes you're right, even without great data, and we confirmed them and greatly solidified the result. Well, you might ask though, all right, we found these objects that look massive and they're black hole candidates, but is there really an event horizon present through which material passes never to be seen again? In contrast to, say, neutron stars where material goes whump, hits the surface of the star and begins to glow. Indeed, well, when we look at these X-ray binaries, those that have neutron stars seem to glow more brightly in quiescence, that is, not during an outburst, than those that we think have black holes. In other words, those that have a hard neutron star surface, the material hits that surface, releases a lot of energy, making it glow brightly. Whereas those systems that have an event horizon, a black hole, trap the material and it doesn't glow brightly. So this is evidence that these systems where dynamically we think that there's a black hole present really do have a black hole because they're fainter in quiescence, not during outburst, than those systems which have a neutron star. In fact, there have been some data that show evidence for the swirling in of material. Swirling in like blobs of material, getting closer and closer to the black hole, fading gradually from sight and becoming more and more redshifted. The light gets gravitationally redshifted. And there's no burst of energy when the thing hits a surface because there is no surface. We think it really went through an event horizon. And this animation reminds me of Poe's story, Edgar Allan Poe's story, A Descent into the Maelstrom, written in 1840. I became possessed with the keenest curiosity about the whirl itself. I positively felt a wish to explore its depths, even at the sacrifice I was going to make. And my principal grief was that I should never be able to tell my old companions on shore about the mysteries I should see. Oh man, he's descending into the maelstrom. You can also get information about the spin of the black hole, and that's because the last stable circular orbit around a non-rotating black hole is at around 3 Schwarzschild radii. But around a rotating black hole, you can have stable orbits that are closer in than 3 Schwarzschild radii. So the gravitational redshift of gas is higher near a rotating black hole than near a non-rotating black hole, because the gas tends to be farther away near a non-rotating black hole than near a rotating black hole. And we do have X-ray evidence of greater gravitational redshifts near rotating black holes than near non-rotating black holes. Additional evidence for spin of black holes comes from these clumps of material that are spiraling in. By measuring them in X-rays, you can get the orbital period and the speed of the blobs, and you can figure out that, in fact, they're so close in that they wouldn't exist unless the black hole is spinning. Non-rotating black holes simply don't allow stable orbits that are such short periods. All the stuff is farther out. Well, some of these objects, in swallowing material from the companion star, form what's called jets. Indeed, sometimes these jets have material flowing out at a good fraction of the speed of light. If you look at an animation of the black hole stealing material from the companion star, you can see the accretion disk, but also a jet of radiation and particles emerging from the vicinity of the black hole. Let me emphasize that this is energy that's being channeled not out of the black hole itself, not from within the event horizon, but rather from a region surrounding the black hole, Newspaper articles and magazine articles often get this wrong. The jet is emerging from the vicinity of the black hole, not from the black hole itself. And a great case of this was a star called SS433. For a long time, we didn't know whether it was a neutron star or a black hole, but in fact, it has two jets like this. You could see them emerging at about a quarter of the speed of light. And more analysis has shown that that compact object really does appear to be a black hole because it has a mass of 16 times the mass of the sun. Wow. Well, black holes, or dark stars, exist. Astronomers are about 99% sure of the existence of stellar mass black holes. It's ironic that Einstein initially thought that black holes were just a mathematical oddity stemming from his own equations of general relativity. Here he is, sad. Perhaps he's sorry that the black holes were even suggested from his theory. Imagine what his reaction would be now if he were alive to see the amazing evidence for black holes. Perhaps his reaction would be something like this. I don't know. Well, though the evidence for stellar mass black holes is strong, we will see in the next lecture that there is even better evidence for a supermassive black hole in the center of our Milky Way galaxy. Stay tuned.